session, we are going to get started with the concepts of data structures in Python. So you're going to understand module number 5, data structures in Python programming language. There are some common data structures which you guys need to explore, which includes list, stacks, queues, tuples, set, and dictionary. These are going to be six important data structures which are available in Python by default. And you can use these data structures to represent data of different types, and then you can perform operations on it. So collection of data, representing data in Python and performing operations is a very important process, because in every algorithm, in every logic, whatever problem you are trying to solve with your programming language, you need to represent the inputs using data structures, and then you have to perform logical operations on it so that you get an output. So now let's see how we are going to make use of data structures in Python: list, stacks, queues, tuple, set, and dictionary. So to get started, we'll quickly go to data structures. Now here, there are a lot of data structures available, wherein we are going to get started with list data structures initially. So let me just put list data structures on one end so that you all will be able to view the documentation during the program. As well as we are going to start Google Collaboratory on one side of the screen so that you will be able to code along with the conceptual part. Okay, so now let's quickly get started. So you're going to go to collab.research.google.com. I believe my voice is audible to all the participants. Please confirm me on chat. So we are going to get started with new Python 3 notebook. Okay, so we are going to get started with new Python 3 notebook. Within new Python 3 notebook, you're going to create a new notebook and you're going to name it as data structures. So I'm going to change it to 8th September data structures. And we are going to get started with a code here. So we are going to implement data structures in Python. So as you all know, data structures are very important, and data structures are used to represent data and perform operations on it. Data structures are used to represent data of different types, and perform operations on it so as to reproduce an output, or it could be a solution to a problem. Okay. So as you all can see, at the right hand side, you're going to explore more on list data structures. So when it comes to list data structures, the list data type has a lot of methods. List is a complex type of data structure available wherein you can represent information of multiple types. It could be integer, it could be string, it could be Boolean, and you can perform operations on these. Okay, so we are going to take up these and we are going to implement certain operations on it. Just before we proceed to list data structures, I would like to take you to another site, which is visualgo.net, which is a one-stop resource wherein you can explore a lot of data structures. And this is a very good resource to prepare yourself for competitive programming also. Now here, we are going to quickly explore linked list. Here in Python, lists, stacks, and queues all are represented using linked list concept. So we are going to use this concept of linked list and we are going to perform implementations. So now when it comes to list, as you all can observe here, there is a list created over here. Okay, so here is a random list created. Now initially what I want to do is I would like to create a user defined list. So in this user defined list, I would like to enter my values. I would like to specify 5 values, 1, 2, 3, 4, 5. So I'm going to click on OK. So now you can see that this is a linked list. So linked list looks somewhat like this, wherein you have a head element and you have a tail element. And all the elements within the linked list are connected to each other. Okay, I hope this is clear to everyone. So now, how can we quickly create a list in Python programming language? So to create a list, we use double square. You use square brackets, and you can pass in your elements within that. So let's say I have passed my elements 1, 2, 3, 4, 5, and I would like to call it as my list. Okay, so if I get the content of my list, before executing this, we need to connect to Google Compute Engine. So let's connect to Google Compute Engine backend, wherein you are going to get 12 GB of RAM and 50 GB of hard disk space. Now, once we are connected, now if we run this cell, you can see that you're going to get the list contents out. Okay. And if you quickly would like to check the type of this my list, so we can call this function type, and we can pass in my list within that. So once we pass this information, and if we print that, you can quickly see that the data type of the variable which we created here, the data type for the variable my list is list type. So here, list is a representation. This is how you can quickly create that in Python, as well as we have created that in an animated format also. Is that clear to every participant? Are you all clear? Great. Now what we are going to do, we are going to perform certain operations on it. Okay. So when you perform certain operations on list, now you need to explore. The first operation we are going to perform is list.append, wherein we are going to add an item to the end of the list. Okay, we're going to add an item to the end of the list. So let's quickly test that. So now what we are going to do, we're going to append an item in the list. So when you append an item into the list, you can quickly call your object mylist, and you can call this function append. Okay, there's a function known as append, and you can add an element. So let's say I would like to append 6 into this list. So here, as you all can see, so append function, we have taken the append function here. This is the list object, which is defined here. And this is the element, which we have specified. So these are the 3 values which you are going to add, which you are going to use in the syntax in order to add an element to the list. I hope this is clear. Now, once you execute this, once you run this, you can see that your data has been appended onto the list. And in the next code block, I would like to quickly check the content of my list. So I'm going to get 1, 2, 3, 4, 5, 6, and 6 is appended on the list. Is that clear to everyone? Now, if it is clear to all of you, now we need to move towards a little technical side of what happens when we append an element on the list. So let's quickly explore that. So I would like to again take you to visualgo.net. And let's say I would like to insert an element. And appending means inserting an element at the end of the list. So if I want to insert an element at the end of the list, I would like to keep the index position as n. Okay. So after tail, I'm going to add in a new element, and I'm going to specify the vertex or the value which I want to add it to the list. So I'll use this option I is equal to n, and I would like to append at the end of the list. So let's say I would like to add an element at the end of the list, and this will be known as 6. Now you need to observe how many operations will be performed when we are going to add an element at the end of the list. Okay, let's have a look. So you are going to watch this in an animated format. Okay, I'm going to keep this a little slow. Now, you all have to observe the animation part here. So when I click on go, when I add an element in the list, so you can see that a new vertex has been added and the tail has been changed to the new vertex. So how many operations have been done here? Let us quickly observe. So you have created a new vertex and you have changed the vertex to the new tail. Okay. Is that clear? So over the list, what we have done, we have accessed the list element and we have just changed the tail of that list. So only one operation has been performed here. Okay. So what we have done, only one operation has been performed here. Let me change the color. So if you all can observe, we have just taken the vertex and we have changed the tail to the vertex, the new vertex, whatever you have created. Okay. So this is only one CPU operation. You can quickly consider it as one CPU operation. And this one CPU operation can be represented as big O of 1. This can be represented as big O of 1. So now you can see that when you try to add an element to the list, it is big O of 1. Because only one operation has been done on the list. Is that clear? So big O of 1 is considered as the time complexity, the time required by CPU in order to perform this append operation. So irrespective of the n number of elements available in the list, if you are going to add an element at the end of the list, it is always going to take big O of 1. Okay, only one CPU cycle is required in order to add an element at the end of the list, irrespective of the size of the list. Is this clear to all of you? Please confirm me on chat. Okay, fine. Now let's see. So now what you're going to do, let me just clear this and let me take you to the complexity sheet first, wherein you're going to understand this thing in a little more detail. So I would like to take you to big O cheat sheet.com. Okay, so here is a resource wherein you guys are going to understand big O complexity first. So here you can see that this web page covers the space and time big O complexities of common algorithms used in computer science. When preparing for technical interviews in the past, the author found himself spending hours scrolling the internet, putting together the best, average, and worst case complexities of search and sorting algorithms. So what he did, he summed up all these algorithms and he has quickly made a website wherein all the time complexity and space complexity of different algorithms are listed. So over the last few years, he has been interviewed at several Silicon Valley startups and also some bigger companies like Google, Facebook, Yahoo, LinkedIn, Uber. And each time that he prepared for an interview, he thought to himself, why he has not created a nice big cheat sheet. So this is very important. Questions are generally asked in the interview questions, wherein whenever you appear for big interviews for big companies. So now here is a quick diagram for big O cheat sheet, which you have to observe here. Now, this is plotted between two important features. The first feature is, let's say you have a data structure and your data structure is having n number of elements. So at the x-axis, we have the elements represented. So consider on one hand side, we are going to have, let's say, 0 elements in the list. On the other hand side, there could be n number of elements in the list. Okay. So this is the range from 0 to n number of elements in the list or in any of the other data structure. And y-axis represents operations. Okay. So how many operations are required in order to perform over those elements. So on the basis of this, we calculated a big O cheat sheet wherein we calculate the time complexity. So as you all can observe, there are 5 types of time complexity available. The best time complexity is excellent. Then you have good time complexity. Then you have fair time complexity, bad time complexity, and horrible time complexity. So excellent is a case wherein your operation is going to be performed quickly, and horrible is a case wherein the operation which you are performing on n number of elements will take a lot of time. So we always have to avoid such situations wherein we have written an algorithm or we have used an algorithm or a data structure which can complete the task in horrible time. We should avoid such situations. Okay, I hope this is clear to everyone. So the objective of a good programmer is he always has to avoid horrible programming, bad programming, and in case if he has options, whatever the best objective for him is, he always have to write a code which can perform operations in excellent time conditions or else in good time conditions. And worst to worst, it should be fair, but it should not be bad and horrible. Okay. So if you all can observe here, excellent time complexity, big O of 1 and big O of log n. These are considered as excellent and good time complexities. Okay. So whenever you write an algorithm, you always have to make sure that, let's say you have a number of elements in a list. Let's say you have 500 elements in the list and you have to perform an append operation. So for append operation, you have written a logic that add a new vertex and change the tail to the new vertex. So it is always going to take only one operation. And hence it's going to be known as big O of 1, which is an excellent time complexity. So append operation on list possess excellent time complexity. Is that clear? Then you have another, which is fair. So big O of n is fair. So big O of n is fair because let's say if you have n number of elements, consider it takes only 1 second to perform one operation on one element. Suppose you have 10 elements in a list, or suppose you have 10 elements on a data structure. And when you are going to perform an operation, it is going to take 10 seconds. And similarly, as soon as the number of elements is increasing in the data structure, the time will increase. So we always have to avoid such situations wherein the time complexity is big O of n or n log n or O(n) square 2 raised to the power n or O(n) factorial. We always have to avoid horrible and bad programming. And mostly you should focus on identifying the best solution wherein you can write an excellent operation or a good operation or a fair operation. But consider there is a bad time complexity. So big O of n log n is known as bad time complexity. And all these are n square, 2 raised to the power n, and n factorial. These are the horrible time complexities, and these situations should always be avoided. Okay. So you should always avoid writing a code which is horrible. Okay. As well as there are algorithms which can perform in bad conditions in case if you don't have an option, but always you need to focus on identifying a solution which can perform the operation in excellent time conditions, good time conditions, or fair time conditions. I hope this is clear to all of you. So now you all need to tell me which is the excellent time complexity. You have to push these answers on chat. Okay, you all have to tell me which is the, okay, big O of 1 is the best time complexity. Okay, big O of 1 is best excellent time complexity. Which is the worst time complexity? the worst time complexity, horrible time complexity. Big O of n factorial is the horrible time complexity. So we should always avoid such situations wherein we write a program which perform operations in horrible time complexities. Okay. Now, let's proceed further. I hope this concept is clear to all of you. Okay. Now let's see. So I would like to take you to another resource now. And this resource is bigocheatsheet.io. bigocheatsheet.io. So over this, you are going to understand the time complexities of various operations which we are going to perform on list. So consider linked list, because we will be using linked list implementation of list in Python programming language. So consider you have a list of n number of elements, okay, and it is going to be a singly linked list. So singly linked list look like this. So there is only a single link from head to the next vertex, then to the next vertex, then to the next vertex. So this is considered as a single linked list. Okay. Now let's see. So space complexity is with respect to O of n, but we will be considering the time complexities. So here, as you all can see, we have done this operation. If you are going to add an element at the end of the list, so that is, you're going to add at the back of the list. So it is always going to be big O of 1 operation. And why it is going to be big O of 1? Because you're going to add a new vertex and you're going to change the tail of list to the new vertex which you have added. So it will take only one operation, irrespective of the size of the list. Is that clear? So irrespective of the number of elements in your list, it is always going to take one operation whenever you're going to add at the end of the list. I hope this is clear to all of you. Is that clear? Okay. So now we have done this append operation, and this operation takes big O of 1 time complexity. And why does it? Why do it? Why is it big O of 1? Because you're going to create a new vertex and you're going to perform only one operation on list, and that is changing the tail from current vertex to the next vertex. So changing the tail is just one single line of operation, and it is going to take one CPU cycle. So it is considered as big O of 1. So irrespective of the number of elements added onto the list, you will be able to perform append operation with big O of 1. Now let's proceed to the next operation. So the next operation in queue is an extend operation. Okay. So before we go to extend operation, we would like to add a few more operations as per the big O cheat sheet. So first one is finding an element in the list. Okay. So we will consider it from here. Let's say first you're going to observe this, finding an element on the list. Okay. And it is known as big O of n operation. And why do we call it as big O of n operation? Let us just quickly explore it. So now here, as you all can see, I have to search an element on the list. Consider the given list is 22, 2, 77, 6, 43, 76, 89, or else I can create a custom list. So let's say I'm going to create a custom list of 1, 2, 3, 4, 5, 6, because I'll be taking the same example as it is available on my Python programming code also on the left hand side. So मान लो आपके पास ऐसा एक लिस्ट है, ठीक है? अब इसमें हम एक सर्च ऑपरेशन परफॉर्म कर रहे हैं. So I am saying I would like to search sixth element on the list. Okay, I want to search the element, the vertex 6. So you all can observe here, I would like to search the vertex 6, which is here. Okay. So when I perform this go operation, let's have a look what is going to happen. So first we have gone to first stage. Let me just keep it a little slow. Okay. चलिए मैं आपको दिखाता हूँ. Let me just keep it at the top. Okay. Now consider. So whenever you're going to search for the element, whatever element you want to search over the list, the first step we are going to do is we are going to go to the head of the list. Okay. So initially you are at the head of the list. As you all can observe, you are going to start your search from the head of the list. Now in the next stage, you're going to match if this item is equal to the vertex which we are trying to find out. If it is equal to yes, then we are going to return the index value. And if it is not equal to, then we will switch to the next vertex. So if I go for the next operation here, okay, if I go for the next operation, you can see that 1 is not equal to the vertex which I am trying to search, and I am trying to search 6. Hence, I am going to change the index and I am going to switch to the next vertex. Now here, the next vertex, I would like to check whether it is equal to 6 or not. If it is not equal to 6, then again, we are going to change it to the next element in the list. So now you all can observe, this is one operation. Okay. We have gone to the head and we have performed first operation on it. We made a check whether it is equal to 1 or not. Then again, we have reached the second element and we performed second operation. Similarly, we have reached to the third element and we would have performed the third operation. Okay. So let's say as soon as we progress further, we'll reach out to the fourth element. Then finally, we'll go to the fifth element. Okay. Consider if you have a list of n number of elements. So finally, at the end, in the worst case or in the average case, you will be reaching to the nth element. Okay. So if you all can see, depending on the number of elements available on your list, the search is going to be performed, and for every operation, there is going to be one cycle used. So this operation will be considered as a big O of nth operation. So if there are n number of elements in the list, n number of operations are going to be performed in order to search an element on the list. Is this concept clear? So if you can see, we'll go to the next element. Then again, we are going to check. We'll go to the next element. Again, we are going to check until we find the last element. Okay. So whenever you try to find an element on a list, it is going to be a big O of n operation depending on n number of elements on the list. So big O of n is considered as a fair big O of n is considered as a fair time complexity algorithm. Fair complexity. Is that clear to all of you? Please confirm me अगर यहाँ तक आप लोगों को clear हो गया है. Okay. So whenever you're trying to perform a search on a list, it is always going to be big O of n operation. Okay. Let's see. So let me just clear that. And now we are going to perform the search operation on our Python program. So let's see. So if I have to perform search for element in Python, what we are going to do? You can quickly check 6 in. So in is a keyword which we use to perform search in the list or in any other data structure or on any other iterable. So I'm going to say 6 in my list. So if I'm going to run it, I'm going to get true response. So that means yes, 6 is found in the list. And suppose if I try to search for 7 in list, in my list. So if you do that, you're going to get a false response. Okay. So using this in keyword, we can perform a search. And whenever we perform a search in Python, it is always a big O of n operation. Okay. It's always going to be big O of n operation. So best case ये हो सकता है कि पहला ही एलिमेंट हमारा वो एलिमेंट हो जो कि हम सर्च करें, तो उस केस में बिग ऑफ 1 हो जाएगी. बट ऑन एन एवरेज केस और ऑन अ वर्स्ट केस, कंसीडर अगर आपकी लिस्ट है और उसका आइटम लास्ट नोड पे अवेलेबल है और जब आप सर्च परफॉर्म करोगे तो इट इज गोइंग टू टेक एन नंबर ऑफ ऑपरेशंस इन ऑर्डर टू फाइंड आउट दैट एलिमेंट. ओके. अब मान लीजिए जैसे आपने एक एप्लीकेशन बनाई. कंसीडर यू हैव मेड फेसबुक में यू हैव गॉट 1 बिलियन यूजर्स. ओके. नाउ इन केस if you are trying to search for a user, let's say आपने मान लो देवांशु शुक्ला नाम का यूजर हम सर्च कर रहे हैं. ठीक है. देवांशु शुक्ला ने जो प्रोफाइल बनाई है, he is the 1 billion user in Facebook. तो अगर हम सर्च करने के लिए हम लिस्ट ऑपरेशन का यूज करेंगे तो इट इज गोइंग टू टेक बिलियन CPU cycles in order to perform that search. Okay. Hence it is going to be a bad program because बिलियन सेकेंड्स अगर लगेंगे किसी भी एक यूजर को सर्च करने के लिए तो पूरा एप्लीकेशन ही फेल हो जाएगा. आई होप यू अंडरस्टैंड व्हाई दिस टाइम कॉम्प्लेक्सिटी इज इंपॉर्टेंट. So whenever you write an operation, the operation should always be either excellent operation or it should be good, and worst to worst case it should be fair, but it should not be a bad program or a horrible program like big O of n log n, big O of n square, big O of 2 raised to the power n, and big O of n factorial. So you should always avoid writing a code which is bad or horrible. Is it clear to all of you? Are you all done till here? Is my voice audible to all of you or not? Now, let's go to the next operation. So accessing first element. Okay. So whenever you try to access the first element on the list. So let's see. Okay. So searching the first element would be something like get the first element out of the list. And whenever you are going to get the first element out of the list, whenever you have to access it. So accessing would be always you need to get the first index. So यहाँ पे तो search operation है, तो whole operation for search is big O of n. But if you try to access the first element from the list, it is always going to be the best case. And it is always going to be big O of 1. Okay. So how do we access an element from the list? Let's see. Access first element from the list. So you can quickly call my list and you can quickly define the index number 0. So this operation is always going to be a big O of 1 operation. Okay. So when we try to access an element from the list, you're going to get the first element fetched out. Okay. Is that clear to all of you? So this is the first element and you all can see this is the response when we try to access the first element out of the list. Okay. So these are the indexes. This is your index number 0. This is your index number 1. This is your index number 2, your index number 3, index number 4, and finally you have index number 5. Okay, so these are the indexes. And this is, you can consider this list as your my list. Consider this is your my list. So whenever you try to access an element, let's say my list of 1, so what is going to be returned? You're going to get 2 in return. Okay, is that clear? So when you try to access this index, you're going to get this response. Okay, is that clear? Are you all done till here? Confirm me on chat. Anybody facing any issues till here? All the other participants, those who are connected. Uday, Virat, Shrestha, Mehta, Pavan, Neha, Kumari. Okay, now. So let's go with the next operation. Now, once you have to access the last element of the list, okay? Whenever you need to access the last element of the list, so you always know the length of your list, okay? And this is always going to be a big O of 1 operation, because you know the length of your list and you can easily access out length minus 1, okay? So hence, it's also going to be the big O of 1 operation. So now you consider access last element from the list. Okay, so you can get the size of the list by calling length function. Okay, there is a length function and you can quickly call it. So this is going to give you the size of the list. Okay, size of the list. So whenever you try to access an element from the list and that is the last element, you can quickly get the length of the list and you can subtract it by 1. And this is also going to be a big O of 1 operation. So you're going to get the last element of the list is going to be 6. Okay. So I can quickly observe. This is the process of accessing last element from a list. Okay. Now, similarly, let us quickly observe accessing an element at an arbitrary index. So when you try to access an element at an arbitrary index, it is going to reach out to that index step by step. And then it is going to fetch out the value at that index. Okay. And I would like to show you how. So let's see. So consider you have this element. So let's say there are certain operations. I would like to simulate with the add operation, and this add operation is similar to accessing the element operation. So whenever you try to insert an element at the top of the list, suppose I would like to enter 10 at the top of the list. So I'm going to add a new vertex and I'm going to change the head. Okay, so this is one single operation. And this is known as big O of one operation. Okay, whenever I add an element at the end of the list, let's say I would like to add 20 at the end of the list. So a new vertex will be added. A new vertex will be added and the tail is going to be changed. So this is again a big O of one operation. But when you try to insert an element at an arbitrary index, okay, so I would like to specify both index and the vertex. So suppose I would like to insert an element at index number 0, 1, 2, 3, 4. At fourth index, I would like to insert an element. So I'm going to specify index as 4 and I would like to insert a value 30. So when I do that, it will start from index number 1 and it is going to go to the next until we reach the index number 4. So you can see that n number of operations are being performed over here, depending on the number of elements available. So we started from here, then we switched here, then we switched here. We have gone to that stage until and unless we reach the nth position, we crawl the n number of elements. Okay. So this operation, inserting at an arbitrary index or accessing an element from the arbitrary index, is always going to be a big O of n operation. But if you try to insert or access an element from the first, it is going to be big O of 1. And if you try to access an element from the end of the list, this is also going to be big O of 1. Okay, is that clear? So now let's say if I try to access an element from an arbitrary index, my list of, let's say 4. So this operation is going to be known as big O of n operation, because it will crawl one by one, it will reach to that element, and then you are going to get that element fetched out. Similarly, when you try to insert an element at an index 4, okay, so you can quickly call this function insert, and here is the syntax for the insert function. So at an insert, you have to define the index. So let's say I would like to insert at index position 4. And what is the value? I would like to insert 30 on the list. And I would like to quickly check back the content of the list. So when we do that, you can see that now at index number 4. So this starts from 0 here, index number 0, 1, 2, 3, 4. So on 4th index, we have got this value 30 inserted. This is index number 4, and this is the value which we inserted. So when you insert at an arbitrary index over the list, this is always going to be a big O of n operation, because every element index by index will be crawled and insertion or access operation will be performed. Clear? Is that clear to everyone? Okay, great. Now let's go for the next operation. So you are done with insert. Now we'll see the remove operation. So when we remove an element, so you can remove the element from the top. Okay. So let's say if you remove the first element, it is going to just delete the temporary and change the head to the next element. So again, it is going to be a big O of one operation. If you try to remove an element from the nth list, now you see, when you're trying to remove it from the nth list, it is going to crawl every element one by one. Okay, until and unless it reaches the last index. And then it is trying to remove the last node. So this operation is going to be big O of n operation. So when you remove an element from the end of the list, it crawls all the elements, and at the end, it tries to remove the tail. So this operation is known as the big O of n operation. So removing from the top is big O of 1. Let's say, I'll write it here. Remove from top is equal to big O of 1. When you remove from end, it is going to be big O of n operation. And when you remove at arbitrary index, it's again going to be big O of n operation. And why is it going to be big O of n? Let's quickly have a look. So when I remove an element from at index position, okay, sorry, I have clicked at the last element, I'm sorry. So I would like to specify the index, and I would like to remove it from, let's say, the fourth index. So once the previous operation completes, we are going to remove it from the arbitrary index. Okay, so let's say I want to remove from index number 4, 0, 1, 2, 3, 4. So fourth element is going to be removed. And when I do that, so again, we'll go to the head, then index by index, we'll go to the next vertex until and unless we found the value available at a specific index. So as soon as the value is found that, okay, you want to remove the value 4, the value will be deleted. And the tail is going to be changed. And this operation is again considered as big O of n operation when you try to remove an element from the list. Is that clear to all of you? Clear? So here you have this operation to remove an element. So you can remove the first item from the list whose value is equal to x. And it raises a value error if there is no such item. So instead of the index, you're going to pass the value. What value element would you like to remove from the list? Okay. And if you want to remove from the index, there is an alternate function known as pop. So if you want to remove at an index, you can use pop. But if you want to remove a value, then you have to call remove function. And removing the first element is always big O of 1. Removing the last element is big O of n. And removing an element from the arbitrary index of the list is again big O of n. So how we do that? Let's say I would like to remove my list dot remove, and I would like to remove 1. So this is the best case. This is going to be big O of 1. Okay, let's run it. So you're going to get my list. Let's quickly search for my list. So you can see that 1 has been removed. Now, what next I'm going to do? Now, what am I going to do? I'm going to remove the element from the last. Remove. I'm going to remove 6. So when I'm going to remove 6, this is going to be big O of n because all the element will be searched, whether the current value at an index is equal to 6 or not. In case if it is 6, you're going to delete it. Okay. So this is going to be big O of n, removing the last element from the list. And now, removing an element from the arbitrary index is again same. My list dot remove, and I would like to remove 30 from this list. Again, this is going to be big O of n operation because all the elements will be searched and will be matched with 30. Okay. Suppose you want to remove the item at the given position in the list, and if you want to return it, which element has been removed, so you can use a pop function. So in pop, you can define an index. Somehow, if you do not define an index, it will remove the last item in the list. Okay. So let's say we have this list 2, 3, 4, 5, and I would like to call this function mylist.pop. And I would like to remove the element at index number 1. So this is always going to be big O of n operation. Okay. And when I do that, you can see that value at index number 1, which is 3, will be removed out of the list. It will be popped out. Okay. So again, let's quickly check back the content of list. So now you are left with 2, 4, and 5. Now, when you try to pop an element from the first index, it is always going to be big O of 1. My list.pop, if you want to remove it from this operation is going to be big O of 1. And you can quickly check back the content of my list. Okay. And if you want to remove an element from an arbitrary index, or let's say if you call pop, so this is known as removing last element. And removing last element is big O of 1. Oh, sorry, big O of n. So when you remove the last element, so it will crawl all the elements and it is going to remove the last element out of the list. Hence, it is going to be big O of n. And you can quickly check back the content of the list, my list. So when you run this, at the end, you get only 4 left out of the list. Is that clear to all of you? Are you all clear with the concepts of list data structures and how do we perform various operations on list? Okay. So there are various other options like clear the list, or you can get the element at an index, you can sort it, you can use count to identify the number of elements. So let's just quickly test all these. So now what you're going to do, suppose I'm going to create a list. Okay. So you're going to create a list with a range function 2 to 20. Okay. And I'm going to save it into my list. And I would like to check the content of my list. So we quickly got a list of elements from 2 to 20. 2 to 19, sorry. I to j minus 1. Okay, let's do it till 10. So we have got a list like 2, 3, 4, 5, 6, 7, 8. We got a list created. Now suppose you want to clear all the elements. You want to remove all items from the list. So there is a function known as clear. And once you do that, you try to access the element in the list. It's an empty list. Okay. So if you want to clear a list, you can quickly call clear function and you can change the list from a filled in list to an empty list. Clear? Okay. Now, suppose we'll go to the next step. In this step, we have to identify the index of a value. So suppose you have a list, let's call it as range. I have got 3 to 20 with step 4. Okay. And I would like to save it into my list. And I would like to print the content of my list. So let's say I have a list of element 3, 7, 11, 15, 19. And I would like to get index of element 11. So over your my list, what you can do is you can quickly call my list. You can call index function just to check at what index value 11 is available. Okay. So when you call this, you're going to get the index value available. So index is 11 at value 11 is available at index number 2. So if you just quickly want to check back out, we'll quickly check the content of my list. And you can see that we have got the correct response. that 11 is at index number 2 because indexes starts from 0, 1, and this is 2. Okay, so you can quickly get the index of a value as well. Now, next, you can count the number of elements available in a list. Okay. Now what we are going to do, let's say we are going to make a list, my list, and I would like to add some element 2, 3, 4, 2, 4, 2, 2, somewhat like this. Okay. So you can see that 2 and 4 appears multiple times in the list. And if I quickly want to check the count of 2 in list, so I can quickly go for my list.count function, and I can provide the element that I would like to check the number of times 2 is available in the list. So 2 is available thrice in a list. So this is the first, this is second, and this is third. Okay, so using count, you can quickly return the number of times X appears in the list. Post that, you can sort the list. We have already used this sort function yesterday. You can call mylist.sort, and you can quickly check back the content of my list. Okay, so initially the list was 2, 3, 4, 4, 2, 2, but now after sorting, this has changed in ascending order. In case if you want to convert it into descending order, you can quickly call the function reverse equal to true. So when you call reverse equal to true, it is descending. So if I run, then I'm going to get 4, 3, and 2. Okay, I hope this is clear. Clear to everyone? Okay, clear. Great. So this is how these operations work. Then you have a lot other operations like copy, which you can use, as well as you can use list as stacks. You can use list as queues. So you can how you can use it as a stack. The list method makes it very easy to use a list as a stack, where the last element added is the first element retrieved. To add an item to the top of the stack, use append. Okay. To retrieve an item from top of the stack, use pop. So stack is going to be the first element which is going to be entered. It's going to be stack has a top and a bottom. So when you're going to insert an element, it is going to become the bottommost element. So whenever you want to add something to the top of the stack, then you are going to use append operation. And when you're going to when you're going to pop the element out, you're going to use the pop function. Okay, so let's have a look. So we are going to explore stacks here quickly. Okay, so now the next operation is using lists as stack. And how does a stack look like? Let's have a look. So this is your stack, and I'm going to create a stack. Okay, so let's say I've got an empty stack and I would like to insert an element 1 on the stack. So when I do 1, I've got an element. Now I would like to push an element onto the stack. So I would like to push 2. So when I push 2 on the stack, okay, you can see that a new vertex has been made, it has been added, and the head has been changed. Okay. So when we do that, so 2 becomes the last element. Okay. So 2 has been appended onto the list. And when you're going to pop, let's say you're going to get pop, so you will get the last appended item removed. Okay. So let's do that. So now what we are going to do, let's add certain elements. I would like to push 2 onto the stack. So when we push a value, it's going to add a new vertex and it is going to change the head. So it is big O of 1. So when you push an element onto the stack, it is big O of 1 operation. So let's add a few more. Let's say I would like to add 3. Okay. So we have got these elements. Now, so when you're going to push element on stack, you have to use append function. Because what append is going to do? Append is going to add the element at the end of the list. And this is big O of 1 operation. Okay. So let's say I've taken a stack, called as an empty stack. And you can use stack.append. You're going to append 1. So once you do that, you can quickly check back. The content of the stack is somewhat like this. It has element number 1. Then again, what you can do, you can append the next element, stack.append. You're going to push in 2 and you are going to check the content of stack. It's going to be 2 has been added. Okay. And if you pop this element, stack.pop, so you're going to get the last element added onto the stack. So when you do that, you're going to get that 2 has been popped out. And only stack is left. Only 1 is left in the stack. Okay. So this is how you all can use list as stacks also. So this is the push operation, which is big O of 1. This is pop operation. This is also big O of 1. Okay. But when we do pop out of a queue, it is always going to be a big O of n operation. Because as you know, it is going to crawl each and every element out of it. Okay. So when we pop an element, it says that it should be a big O of 1 operation, the stack. But when you use list as a stack, then it is always going to be a big O of n operation when you do that here. Hence, using stack is not preferred. Using list, it is not preferred to make list as a stack, but there is an option. You can do that in Python. Okay, but the performance will not be good. Now, similarly, you can implement stacks as queues also. So for this, we have DQs available. So you can see that it is possible to use list as a queue, where the first element added is the first element retrieved, first in, first out. However, lists are not efficient for this purpose. While appends and pops from the end of lists are fast, doing insert or pop from the beginning of a list is slow, because all of the other elements have to be shifted by 1. To implement the queue, you can use collections.dq, which will be designed to have fast appends and pop from both ends. So what you can do, you can make use of this library collections, and within collections, we have stack, queues, DQs, every collection like a data structure available. So you can import dequeue from it. You can create a queue using dequeue operation. Then there are functions to append, to add an element at the end of the queue, and you can call pop left, which is going to remove the first element out of the list. Okay. So let's see how you're going to use queues in Python. Okay, let's go for it. Now we are going to define using queues, using lists as queues in Python. So from collections library, you can import the queue. Okay, from collections, you can import the queue. And you can call this dequeue function, and you can get the list. Okay, so let's say I'm going to make a list of names. Let's say there is a railway reservation system wherein Ajay came first in the queue, and I'm going to call it as queue, and I'm going to get the element out. So as soon as the first user reaches, we got Ajay added into the queue. Now, in case if we got second person, we're going to append in the queue. So let's say I'm going to call Vijay will come in the queue. And I would like to check the contents of the queue again. So now you can see that Ajay is the first and Vijay is the second. Similarly, let's say we appended one more queue.append. Let's say Shyam, let's say, and we're going to check the contents of the queue. So Ajay, Vijay, Shyam, they are now in queue. And now once reservation of Ajay is already done, so he need to leave the queue. So in that case, we're going to use this function pop left. Okay. So here is the first out. This is the first out operation. So after this, we're going to get the queue checked. So when you pop left, Ajay has his reservation has been done, so he will be removed out of the queue, and the left out person, Vijay and Shyam, are going to be left in the queue. So Vijay is now on priority number 1 and Shyam is on priority number 2. So you can use list as queues also. So I hope this is clear to all of you, how you can make use of data structures like list, what all operations you can perform on it, how you can understand the time complexity, as well as you can use list as stacks and queues in Python. I hope this is clear to all of you. Please confirm me on chat. And I'm sharing link to my script so that you all can observe and you can quickly execute these. Okay, everyone, if it is clear, please confirm me on chat. Great. So that's all for today's session on stacks, queues, and list, and on time complexities. In next session, we'll get started with list comprehensions. Thank you so much for watching.